I am Neha Duhan from Indian Institute of Technology, IIT Roorkee, India. So I am currently working on the simulations of dislocations using extended finite element method. So in this manuscript, I have worked on XFEM simulations of dislocations in silicon germanium alloy under thermal loads. So in this presentation, I would like to give a brief introduction about the semiconductor materials dislocations and then overview of the work which is already been done considering the continuum mechanics point of view, and then the formulation of this mathematical framework, numerical example and conclusions. So proceeding with the introduction. So what are the semiconductor materials? Semiconductors are the crystalline materials which are having material properties in between conductors and insulators. So mainly these are divided into two parts, broadly classified as intrinsic semiconductors and extrinsic semiconductors. So intrinsic ones are pure materials, they are not having any impurities. But extrinsic ones are having impurities in the form of doping or alloying. So in the form of doping, if the electrons are more, it will be called N-type or N-doped semiconductor. Otherwise, if it will be a P-type. Also, alloying is done by considering two types of semiconductor materials. So in this manuscript, I am considering the alloy of silicon and germanium, where SiX, Ge1-x. So, considering about the crystal structures, there are two crystal structures mainly for the semiconductors. One is for the zinc blend sphere-like kind of crystal structure. Another one is the woodgite, which is nothing but the HCP. So for our alloy, which is under consideration, it is the first one, zinc blend or sphere-like kind of crystal structures. So now, where are the defects? Where is the dislocation in this crystal? So these are crystals which are made of atoms, and if there are some atoms missing or there are some extra atoms, then there will be defects. So considering the line defects, they are mainly classified as S dislocations and screw dislocations. So considering S dislocation, we are having the Burgess vector perpendicular to the line vector, which is along the dislocation line. So and screw dislocation will have the two vectors as parallel to each other. So considering the continuum concept of dislocation, so Vito Volterra in 1905 gave the continuum concept. So how to model dislocation considering the continuum mechanics point of view? He defined that if we consider a hollow tube and if we define its coordinate axis as x, y and z, and if we cut it in the xz plane and give displacements in y direction or in x direction, then this will form S dislocations. Or if we give movement in the z direction, it will be of screw dislocations. So this is the important concept which we will be using considering the continuum concept of dislocations. So now why I am opting extended finite element for doing the simulations of dislocations. So for this, as we know, every system has some governing equation. Similar is the case for dislocations. And analytical solutions are not every time possible with the dislocation, so they are having non-linearities, also complex loading conditions. So we are considering numerical methods for various parameters considerations. So mainly for dislocation, as of now, people are using FEM and XFEM. So I am considering the XFEM so that we can model the singularities and singularity at the dislocations core. So here, overview of the work, and as of now, dislocations has been modeled considering the continuum concept for the elastic case for obtaining the primary and secondary fields using XFEM. Then thermoelastic analysis of dislocation dipoles, dislocations near free surfaces, and the biomaterials has already been done. So mainly the contribution of continuum mechanics to the dislocation was earlier started by the Professor Gracie in 2007. He defined XFEM for dislocations, and then various works has been done. So other than that, electroelastic modeling of dipoles has also been done. Other than that, effect as the dislocation we are considering the semiconductor materials, they are having electric field around the dislocation core, so that will generate heat. So that joule heat will be considered near the dislocation core. So for this work, this will be the formulation, like we will need some basic equations for any any problem, there are some equations for this. If we consider a body which is having domain omega, having the boundary gamma, so over this boundary, if there are equilibrium equation, as we are considering the thermal loads along with the elastic field, so we will be considering the equilibrium equation of force and the heat. Here small q represents the heat flux, capital Qj represents the joule heating due to the electric fields. Here gamma represents the electrical conductivity of the semiconductors, and then we will need the constitutive relations which will relate the stresses with the strains and the heat flux with the temperature gradients. So this will be the equations which will be used along with the equilibrium equation to define the weak formulation and the discrete formulation of the problem. Here this epsilon ICM is the mechanical strain tension, which will be the total strain minus thermal strains. Then we will need boundary conditions, which will be in the form of essential boundary conditions and natural boundary conditions. Essential boundary conditions will be defined in the form of temperatures or displacements, and the natural boundary conditions will be defined in the form of heat fluxes and traction. So now to consider the discontinuity along the glide plane, so this will be called the glide plane, the black one, and the dislocation core will be considered, is represented by this red color as dislocation symbol. So the discontinuity along this glide plane will be considered with the help of Heaviside enrichment function, and the core enrichment will be done with the help of these functions defined by Professor Gracie. So these are nothing but the displacements at the core which are obtained for the presence of a dislocation in an infinite material. For that case, these kind of enrichments will be applied in the FEM formulation, and then it will become an extended finite element method. So now we know the weak form. So finally, after considering the equilibrium equation along with the constitutive relations and then considering the concept of virtual work principle, so we can define the weak form in this way. So even the left side is arranged in such a way that it will give the stiffness matrices, and towards the right side the forces are arranged. So if we now substitute these primary variables, which is temperature and displacement, in the form of approximate field equations, so those equations then are defined with the help of shape functions, and NT is defined for the thermal field, N is for the displacement field. So and then the derivatives are defined with the help of D, BT and D. So BT is the derivative of shape functions for the thermal case, and D represents the derivatives of the shape functions for the elastic case. So now these equations can be simplified in the form of KTT equal to FT and KU equal to F. So these are the two simplified equations which we need to solve to obtain the solutions for the temperature field around dislocation and for the displacement fields within the material around dislocations. So first we will solve the temperatures, and then we will consider the thermal strain from the thermal strains here, and then we will solve it for displacement. Then after we know the primary variables and the secondary variables, we can directly calculate the peach collar force. Peach collar force is the force or dislocation because of the presence of the stress field other than the stresses of the dislocation itself. So for that the concept of J integral has been applied. Other concepts are also there to calculate the peach collar force, but for the simplicity to use it with the help of finite element method, J integral equation has been specified. So this will be the J integral equation for the path independent form, but as we know the elements are we are considering the elements here, so domain form, area form will be better to use with the FEM. So it has been converted to the area form, and here a function is used, W is used, which will be 1 over the internal surface, and it will be 0 over the outer surface to calculate the peach collar force. Now this shows the overall procedure to solve this problem. First we will need some inputs. For those inputs we will need some geometrical data, we will need material properties, we will need boundary conditions. All those are first defined, and then the XFEM model under plane strain condition has been considered here. Then we will define some element types, we will create the mesh, After that, we will identify which nodes are over the glide plane, which nodes are at the dislocation core. So those nodes will be identified, and then at those nodes the enrichment functions will be defined, and so that the shape function will be modified. So considering the shape function over a global matrices are obtained as KT and FT, which will be solved by applying the temperature and heat flux boundary conditions. We will get the solution for the thermal field. Considering these thermal strains, we will then consider those here for the calculation of the forces in the displacement field. So for that we will calculate the global stiffness matrices for elastic case. Then we will define the forces due to Burgess vector over the dislocation, glide plane and thermal strains, and those will be considered to obtain the solution of displacement. Then these displacements will be post-processed to obtain the heat flux, stresses and pitch collar force. So main aim is to obtain the pitch collar force so that we can know the intensity of the dislocation motion. So here we have considered an edge dislocation in a semi-infinite domain which is having a free surface over to its left, and all other three surfaces are part of the infinite body. So for correspondingly the displacement fields of a dislocation in these three surfaces will be applied so to indicate that this is a part of infinite body, and the temperature thermal phase will be applied in two forms. One is for the heat flux perpendicular to the glide plane, another will be to heat flux parallel to the glide plane. So for heat flux perpendicular to the glide plane, it shows the blue line shows the we were applying temperatures over here. So bottom surface will be given the negative temperature difference, upper one will be given the positive one. And then for the heat flux parallel to the glide plane, we will apply the negative heat flux on towards left, negative temperature on left surface and positive one on the right surface. So and correspondingly we will use here, as it is a part of the semiconductor alloy, so silicon germanium. So concentration of silicon is considered as which will be affecting the material properties. So lattice constant is defined in the form of the concentration of silicon in the alloy. Then the thermal expansion coefficient is also defined in the form of with the help of Xg, which represents the concentration of germanium in the alloy. Thermal conductivity kappa is also defined as with the help of Xge, and the elastic material constants are obtained with the help of rule of mixture by considering the elastic properties of silicon and germanium. Here are the elastic properties which are taken from the literatures. Now, to solve this problem, it shows the outer red squares are showing the external boundaries. Here magenta color shows the dislocation core, blue color shows the nodes which are present over the on the elements which are on the glide plane. So to consider this, these are the expressions which are used, which are analytical solution of a dislocation present in a semiconductor, a semi-infinite body. So the corresponding to that, Ux and Uy will be applied over these three surfaces with the help of this equation, where X and Y are defined at the start of the glide plane, and small d is nothing but this length of the glide plane of the dislocation core. So number of elements are given here. So after applying these boundary conditions, we will solve the problem. We have calculated the pitch collar force with the help of J integral, and then here we are we are plotting the normalized pitch collar force, which is normalized by dividing the numerical values with the analytical elastic pitch collar force for x equal to 0.5. So here we show we have considered different temperature boundary conditions, and we have considered different silicon concentration for different alloys. So as we see, as we increase the silicon concentration, the pitch collar force of dislocations are increasing for all the cases. And as we increase the temperature, the amount, that is the value of the pitch normalized PK force is also increasing in the upward direction. Here, if this was the case for the heat flux normal to the glide plane, when we had negative temperature at the bottom surface and positive one at the top surface. This one is the case when we are applying the heat flux parallel to the glide plane. So here also we can see the trend that as we increase the silicon concentration, the intensity of the forces, pitch collar forces are increasing. But for the case of increase in the temperatures, there is very less effect, like if we see at the high concentration, but we can see at the lower concentration as the temperature increases, the free spoiler force is decreasing. Now the summary and conclusion, as we see that we have studied the silicon and aluminum alloy with an edge dislocations which are subjected to thermal loads in the form of external heat flux and electric field induced Joule heat. We have considered the 2D plane strain analysis and the Voltaire type of dislocation has been modeled using XFEM by considering the Joule heat. Then material properties were functions of silicon concentration. This concentration is varied from 0 to 1 and temperature is varied from 300 to 500 Kelvin. And we have found that there is an increase in peak polar force with an increase in silicon concentration above 0.2% for both the cases. But we can see here that below 0.2% there is a little different behavior for two cases, I mean for the heat flux in different directions. So I would like to acknowledge Indian Institute of Technology for funding this ECF 23 to travel here, and these are the references, and thank you.
Okay, we have time for one question or two short questions.
So what you're simulating is not an iterative approach, right? So you first compute the temperature field, and then you compute basically the stress field.
Yeah.
And because of that, I would expect that maybe the dislocation starts moving, and that would have an effect again on the temperature field and the stress field. So you would go for a bit of. But you're not doing this, you're doing this a one-time forward simulation. Right? So is that important or not?
Yeah, as of now, it's like at one point only I have calculated it, but for motion of dislocation, we can, obviously we were planning to do it in the future, like how it will then affect if dislocation is moving frame by frame. Then. As of now, at only one location.
Like,
I was wondering, did you compare with the standard finite elements computation times? And do you use the same integration scheme for the rich elements and the bulk elements, so to say?
Similar to as we do the crack modeling with the help of XFEM, we use the like subtriangulation for
the diagonal triangulation.
Yeah, that kind of thing is also done.
Okay, thank you. Okay, if there are no more questions, we thank the speaker once again. Thank you.
Thank you.
And now we move on to